Now, this video discusses about what we call the equations of a plane. So, what is a plane? If we say a plane is said to be a flat surface on which a straight line joining two or more points can actually wholly lie on it. That is what we call actually a plane. Now, let's say we have a three-dimensional coordinate system. Let's say we have a three-dimensional coordinate system. Let's say this is the case. Now we should understand that this is z-axis and that this is y-axis and that this is what we call the x-axis. Now let's say we have a plane. Let's say we have a plane that is going like that. Let's say this is the plane. Let me have it in this way. Let's say we have a plane let's say this is a simple plane we can have. Let me have it proper here. Let's say this is a simple plane that we can have. Let's say it has to go like that. You know, this is a typical example of a plane that we can actually think of having. Of course, I'm not much impressed with the way it is here. Let me just have it, whichever the order. Let me just have it in this way. Otherwise, I'm not fully impressed with how it looks like, but let me have it in this way. Much as it will make sense, then it will be okay. Let's say this is a typical plane. And let's say within the plane we have a point. I'll call it as, let's say, a point P naught. And let's say the coordinates corresponding to the point P naught. And let's say I'll have them as x naught, y naught, and also z naught. These are the coordinates corresponding to the point P naught in that way. And now let's say we have another point. Now I'll call it as a point B. And in this case, let's say the coordinates at the point B are given as x, y, as well as z, that way. Let's say that is the case. Now let's think of expressing the position vectors with respect to these points. It should be with respect to these points. And let's say we have a position vector. And let me use actually this ink. Let's say we should have a position vector. Let's say this is the origin, by the way. You should have that. This is origin. Now we have a vector OP in that way. But let me present a vector OP, let's say, being given as R. Let's say the vector OP should be given as R naught. It should be vector R naught. Equated as a vector R naught. It should be in that way. And also, let's think of having a position vector with respect to point P. Let me call that one as, let's say, vector R in that way. And let's think of expressing the point P naught as well as the P in terms of the vector. Let me connect a line, or have, let's say, that is the line. And in that case, so now as you can see there, the vectors are head on to tail. This vector is hold on to tail with this vector. That is a vector P not P, where this is the resultant. Now let's think of having the triangle of adding vectors. So you see that the vector OP should be OP naught plus vector PO should be P naught, or actually should be a vector P naught P is the same as vector OP. That is according to the triangle of adding vectors. So what is vector OP naught? We have it as R naught. We have it as R naught in that case. And what is the vector P naught P? That is, we don't know how it will be, but it is given as that. And what is the vector OP? It is given as the vector R. Now in this case, let's think of expressing what is a vector P naught P. You see that the vector P naught P, it is given as the vector R and minus that of the vector R naught. That's how it will be. So which means a vector, actually a P naught P, it is given as the vector R, and the minus vector R naught will be given as that using the triangle of adding vectors. So keep that in mind. Let me take it out here. Now there is something you have to understand about. And what is that? Now let's say we have a vector which is perpendicular to, let's say, that vector which is perpendicular to this vector. Let me have it as this. Let's say this is the vector, and which is perpendicular to the vector. Let me use another key, and for the further clarification. Let's say that is the vector of interest, and let's say it is perpendicular to this actually particular vector. And let me call this vector as the normal vector, given as that. And let's say it is given with the components given as A should be, a B as well as the C. These are the components of the normal vector, actually N. Now the fact that this vector, this vector P naught P, it is let's say on the plane, and it is the fact that the vector P naught P, it is on the plane, and it is perpendicular to the vector, normal vector given as N, then you have to understand that this vector, actually a normal vector, is also perpendicular to the plane as well. The fact that it is perpendicular with respect to this vector, then the vector itself, it is also perpendicular to the plane itself. Now from here we can be able to come up with equation of a plane. Now how should you have the equation of a plane in this way? So now the fact that these two vectors are actually perpendicular, or we say they are orthogonal, then this principle will be actually a true. Mind you, if we have two vectors, let's say a vector A and a vector B, and being that they are actually perpendicular, then their dot product has to be equal to 0, and that is true for actually perpendicular vectors. Now in that case, we'll have, a normal vector n dot should be dot a vector r minus the vector r naught, and that will be equal to 0. And since the vectors are actually perpendicular vectors, now this is how we should have to understand about how we can get it up to the equation of a plane. So we just need the normal vector, and also we just need the single point. But let me have it properly. What is a vector n? So now the vector n is given as, a, b, as well as c, and the dot of which, what is the vector r? Now the vector r, it is the position, a vector with respect to point b. Now the vector r will consist with the components given as x, y, as well as z, like that. And the minus, what is the vector r naught? Vector r naught, it is the position vector with respect to the point b naught, and that will have it as x naught, y naught, and also z naught. We'll have that, and which is equal to 0, of which we can be able to subtract these vectors componentry. So that is to say, we'll have, a, b, c, like that, and the dot, we'll have it as x minus x naught, and the y minus y naught, and also z minus z naught, and which is equal to 0. This is what you call the vector equation of a plane. This is what you call the vector equation of a plane. Now, apart from having the vector equation of a plane, we can also be able to express the equation of a plane in form of, the scalar value. So there are three ways in which the equation of a plane can be expressed. We have what you call the vector equation, and also have what you call the scalar equation. So what is a scalar equation? A scalar equation is obtained upon having the dot product of this vector as well as this vector. So in that case, we'll have it as, a times x minus x naught, and that plus b times y minus y, actually it should be y minus y naught, like that, and the plus c times z minus z naught, and which is equal to 0. This is what you call the scalar equation of a plane. And now, apart from the scalar equation of a plane, we also have another, a way of presenting the equation of a plane, and that will be obtained upon expanding and expressing whatever we have here, and that will be given as ax plus by and plus cz and plus d, which is equal to 0. So this is what you call it as a linear equation of a plane. So there are two ways of expressing the equation of a plane. That is what you call the vector equation. The vector equation, that is, and we have what you call, that is a scalar equation. That is a scalar equation, like that. And we also have what you call the linear equation. So keep that in mind, linear equation. Now, these two equations are derived from the vector equation. So as you can see, we just need the normal vector to the plane and that of a single point in order to come up with the equation of a plane. Now, let's try to have the following cases and appreciate how we can have it. Find the equation of a plane that passes through a 2, 4, 3, and with a normal vector, let's say given as, I'll have it as 2, 1, 0. Now, how should you have the equation of a plane in this case? So first thing, we have a single point, and the single point gives us x naught, that is given as 2, and we have y naught, that is given as 4, and we have z naught, that is given as 3, and we have a normal vector that is now will give us the value of a, that is 2, and we have b, that is given as 1, and we have c, that is given as L. Now we should have to express the equation of a plane, and preferably let's express the equation of a plane actually in form of the linear equation. And what is that one? So first thing we should have to express it as a scalar equation, that is given as a times x minus x naught plus b times y minus y naught, and plus that of c times z minus z naught, that is given as to be 0. And what is the a? We have it as 2 times x minus, what is the x naught? We have it as 2, and plus what is the b? We have it as, so what is the b? No b, we have it as 1, no times y minus, what is the y naught? And we have it as, that is given as 4, like that. And plus what is the c? We have it as L times, and how about that of, so we have z minus, and what is the z naught? We have it as 3. And by the way, this normal vector has to be, we should have some value here. Let me have it as 3, so which means c will be given as 3, and the c should be given as 3, and such that I should have here 3, so which means we'll have 3 in that way, that will be given as L there. Of course, this is actually the equation of a plane that we are looking for. Let me further express that one, and I should present it in form of linear equation. But sometimes it is always being specified that you should have to come up with the equation of a plane in this form, in this form, in this form. But if it is not being specified, it is most preferable to present it in form of linear equation. So have it as 2x minus 4, and plus y minus 4, and plus 3z minus 9, which is equal to 0. And I'll have the like terms together. I'll have 2x, of course, plus y, and plus 3z, and negative 4, that is negative 8, negative 8, negative 9, that will be given as negative 17, and which is equal to 0. Now this is what you call the equation of a plane that we are looking for. And let's have another question and proceed. And let's say question B says that we have a plane passes through, let's say 1, 5, 10. Let's say that is the case, and with a normal vector, and that is given as, let's say, 2i minus 5j, and plus 6, let's say k. Now how should you have that? Principle remains the same. We have a single point, and that will give us x naught, that is given as 1, and y naught, that is given as 5, and the z naught is given as, let's say, 10. And now we have a normal vector, and that is giving us the value of a, that is given as 2, and b is given as negative 5, and c is given as 6. Then now we should have to come up with the actual equation of a plane in that way. So try to have it out how we can have it. Now another question, I'll go ahead as question 2. Find the equation of a plane with the following points. Find the equation of a plane with the following points. Let's say we have a plane. Let's say we have a plane, assuming that it is on a 3-dimensional coordinate system in that way. And let's say we have been given 3 points on the plane, right? Let's say this is a point B, this is a point Q, let's say this is the point R in that case, and we have been given their respective coordinates in these points. Now, how can we be able to determine the equation of a plane if this is the case? So mind you, all we need to have the equation of a plane, we need to have at least a single point. It's enough. And we need the normal vector. But now we're being given 3 actual points. So how should we have that? So first thing, we will choose a single point of our interest. Let's say our interest is to make use of the point Q, and which is okay. Let me have it as x, y as well as z. Let's say that is the case. Should be x naught, y naught. Should be x naught, y naught as well as z naught. So you can choose whichever the point of our interest. And someone can choose a point P presenting that one and the point R presenting that one. And the next what we need is to have the normal vector. So how should we have the normal vector? The first thing, we should have to express any 2 column vectors we can have from the plane. Let's say a vector should be PQ, and let's say another vector given as a vector PR. So we'll have to express these 2 vectors, vector PR and the vector PQ. Any 2 vectors will be enough. And from there we'll have the cross product of the 2 vectors. And much as you know that the cross product of the 2 vectors gives us the normal vector, should be much as you know that the cross product of the 2 vectors gives out the vector which is perpendicular to the 2 vectors, and hence that vector will also be normal vector to the plane. And mind you, these vectors are on the plane. This vector also is on the plane as well. But now, since upon having the cross product of the 2 vectors, we'll have a vector that will be perpendicular to this vector as well as that vector. And much as that vector will be perpendicular to these 2 vectors, then that vector also be perpendicular to the plane as well. And hence that one will be given as a normal vector. So now we need to have the cross product of the 2 vectors. So vector PQ and the vector PR. And the cross product of the 2 vectors will give us the normal vector to the plane. So now before having the single point and the normal vector, everything will be land smooth. So keep that in mind. And now let's say we have 3 points on the plane. Let's say we have a point S that is given as 2, 3, 4. And we have a point R that is given as 0, 5, let's say 7. Let me have it done here. And we have a point Q that is given as 1, 1, 1. So what is the equation of a plane in which these 3 points are lying on? How should you have that? So first thing, we'll have to express any 2 column vectors, and with respect to these 3 points. Let me have a vector SR. That is for the sake of interest. So what is the vector SR as the column vector? We'll have it as, we have it as 8, that is 10 minus 2. And 5 minus 3 will have it as, 2. And 7 minus 4 will have it as 3. That is the first column vector. And I should have SQ. To have the vector SQ. What is the vector SQ? And 1 minus 2, that is given as the negative 1. And 1 minus 3, negative 2. And 1 minus 4, that is negative 3. So that is the column vector we have. Then I will have the normal vector that will be obtained upon having the cross product of the 2 vectors. Upon having the cross product of the 2 vectors. So have the normal vector. And then we choose any single point, among these points. And that will be used to have the equation of a plane that way. So that's how you should have to get it in that way. Keep that. And now let's have this case Let's say we have, this is a plane, and let's say we have a plane, that is the case, and we have a point on the plane. I'll call it as, let's say, a point P, and let's say there is a line, there is a line, and which is perpendicular to the plane. Let me have it properly. Let's say there is a line which is said to be perpendicular to the plane. Let's say the line is said to be perpendicular to the plane, and let's say the line is being given with symmetric equations given as, let's say, x is equal 5 minus 2t, and y is equal, let's say, negative 1 plus 5t, and z is given as, let's say, 6, let's say given as 16. Now let's say the point on the plane, it is given as, let's say, 1, let's say 2. Let's say that is the case. Now how can you be able to determine the equation of a plane if this is the case? That is, when the plane is perpendicular to the line in a space. How can we have the equation of a plane? So principle remains the same. All we need is that for us to come up with the equation of a plane, we just need a single point. Just need the single point, and we need the normal vector. Just this. So nothing much. And of which we have a single point that is given as a point P. But now what we're looking for, it is the normal vector. Now how should we have the normal vector if this is the case? So now you have to understand that wherever there is a line in a space, always there is a vector which is parallel to the line, and that vector is said to be directional vector. Now, what is the directional vector with respect to this line? And mind you, directional vector, it runs parallel to the plane. Actually, it runs parallel to the line. So in this case, the directional vector of the line is given as negative 2. You can have it as 5 and 6. This is the directional vector of the line, and it is parallel to the line. Now, since the line is parallel to the plane, in that case, and also the same line being parallel to the directional vector, then you see that the directional vector will be, since the line is perpendicular to the plane, in that way, and also being that the directional vector, it is parallel to the line, then from the fact that the line is perpendicular to the plane, then the directional vector also be perpendicular to the plane as well. If that is the case, then the normal vector to the plane, it is the same as the directional vector of the line. And since this directional vector is parallel to the plane, and since the direction vector is parallel to the line, and at the same time the line is parallel, it is perpendicular to the plane, then the directional vector will also be perpendicular to the plane as well. Hence, that one will be regarded as the normal vector. So keep that in mind. So whenever the plane is perpendicular to a line, so the directional vector of that particular line, it is the normal vector for that particular plane. Keep that in mind. Let's say we have a plane, and which happens to pass through the point. I'll call it as 2, 4, let's say 2. And the plane is perpendicular to a line with symmetric equations given as 2, minus t. Let's say y plus 5 minus 5t, and z is given as, let's say, 1 plus, let's say, 8t. Now, what is the equation of a plane? Now, first thing, we have a single point on the plane that is been given as that. And what is the x naught? X naught given as 2. And what is the y naught? We have it as 4. And what is the z naught? We have it as 2. Then what we need is the normal vector to the plane. Now, the fact that this line is normal to the plane, then the directional vector of this line is also normal to the plane as well. So if that is the case, the directional vector of the line, it is the same as the normal vector to the plane. So what is the directional vector of the line? We have it as -1, like that, -5, and we have it as 8. So that is the same as the normal vector. That will be given in the same way, -1, -5, and a comma 8. So now we have the normal vector in the single point. We can be able to come up with the equation of a plane in that way. Now, what if the plane and the line are parallel? Let's have this case. Let's say we have, this is a plane, and let's say on the plane we have a single point. I'll go it as a point P with a coordinates, let's say x naught, y naught, as well as z naught. And let's say we have a line which is parallel to the plane. Let's say that is the line. And let's say the line has been given, let's say the line has been given, let's say, in terms of the parametric equations. That is given as x is equal to 5 minus t, and y is given as -2 plus, let's say, 2d, and as z is given as, let's say, -1 minus, let's say, 3d. Now, how should we have the equation of a plane if that is the case? So we have a line and which is parallel to the plane. We have a line which is parallel to the plane, and we have a single point on the plane. How should we have the equation of a plane if this is the case? So we know that the equation of a plane needs us to have a single point, that is, as we already know, and we need to have the normal vector. Okay, we need to have the normal vector. So this information will be enough. So we have a single point right this, which is given as this. Now, how should we have the normal vector if that is the case? Now, our interest will be on the a line. We are going to develop 3 equations from the line. And what is the first equation? The first equation that we are going to develop 3. Actually, I should say, we are going to develop 3 vectors from the line. We are going to produce or develop. I should say, we are going to produce or develop 2 vectors from the line, and of which the first vector will be given as the directional vector of the line, and that much you know, it is always parallel to the line. And we'll have it as directional vector being given as, -1, we have 2, and -3. And we're going to come up with, we'll have to come up with the any 2 points from the line. And how do we deduce the points from the line? Let's say we have, this is a point Q. Let's say this is, I'll have it as a point R. So at the point Q, let's say we have a value of t being given as 1. Mind you, in case you missed out how we deduce the point on the straight line, just have to refer to my previous videos and check it out, how we determine the points on the line in a space. So let's say the value of t is given as 1. Now what are the coordinates of the point Q? So substitute, we'll have, have it as a 5, we'll have 0, we'll have it as -4. Those will be the points. I should say, these are the coordinates at the point Q. Then at the point R, we should let's say the value of t should be given as, let's say, 2, or even 0 as well. Let's say t is given as 0. So in this case, we'll have the coordinates given as 5, -2, and the -1. These are the coordinates. Then you are going to express the column vector QR from these 2 points. So have the vector QR from those 2 points. And what is the vector QR? We'll have it as, have 0, and we'll have -2, and we'll have it as -3. Now this is the vector QR. Then we'll have the cross product of these 2 vectors. We understand that the cross product of these 2 vectors will give us a vector that will be perpendicular to the line as well as the plane. So the cross product of the 2 vectors will give us a vector that will be perpendicular to the a line, and also perpendicular to the plane as well, since they are parallel. Mind you, according to the principle behind, if we do the cross product of these 2 vectors, we'll have a vector that will be perpendicular to this vector and also to this vector as well. And since the vectors are on the actual line, then it means you should have to know that this direction vector and the vector QR are also parallel to the plane. Now, if the vector obtained upon having the cross product of these 2 vectors will be perpendicular to these vectors, then that vector also be perpendicular to the plane and also to the line as well as to the plane as well. We'll have that. So have the cross product of these 2 vectors. Mind you, this vector actually, this vector, direction vector, it is parallel to the line, and since it is parallel to the line, it is also parallel to the plane as well. And this vector QR, it is also on the line, much as being parallel, and also it is parallel to the what? It is parallel to the plane. And since the vector obtained upon having the cross product with the vectors will be perpendicular to these 2 vectors, then it also be perpendicular to this line and also perpendicular to the plane as well. We'll be able to defeat that one. So keep that in mind. So lastly, you should have to try this at your own time. Let's say we have a plane with points given as 1, 2, 5, and the plane is we should have a plane passes through this point, and it is parallel to the line with symmetric equations given as, should have it as, should be parametric equations given as x is equal, let's say 2d, y is given as -5d, and z is given as 1 minus 60. And let's say we have a plane that passes through, let's say 0, 1, 2, and it is parallel to the line, passes to the line, passes through 1, is parallel to the line, passes through 1, 1, 1, 2, 15, 1, like that. There should be that. So how should you have the equation of a plane if that is the case? Thank you.